In this talk by Klaus, Havelund, and Doron Peled, we represent the use of BDDs in runtime verification. BDDs is a data structure for the compact representation of Boolean function. So the main goal is to represent a Boolean function with a small amount of memory. But in addition, BDDs are equipped with a bunch of procedures that allow us to process and combine BDDs. Because of that, BDDs were shown to be very effective in the analysis of systems. In model checking, the symbolic model checking using BDDs were shown a huge expansion of the size of the state space that can be analyzed, from millions of states to a huge number of states. In runtime verification, BDDs were shown to be able to help us to analyze traces with a lot of data. So let's think about a binary tree. We see here on the slide a binary tree that represents a Boolean function which is parity. That means it's the sum of 3 bits, x1, x2, and x3, modulo 2. The function's variables label the non-leaf nodes, and the leaves contain the results of the function. Now the size of this tree is exponential in the number of Boolean variables or bits. So we want to achieve a much more compact representation. And the idea of BDDs is that we want to combine subtrees that are isomorphic to each other and represent them just once. So we get a directed acyclic graph or DAG instead of a tree. BDDs were introduced by Bryant in 1986. They often allow a concise representation of Boolean functions, but not always. This can depend on the variable ordering, as we're going to see. However, there are examples of Boolean functions, for example, Boolean functions that represent binary multipliers that cannot be reduced, that have a BDD representation that is not very small. However, given a Boolean function in a particular order on the variables, there is only one BDD representation. So there is a canonical representation that depends on the variable ordering. And it's very nice that we can apply Boolean operators using procedures on BDDs in polynomial time and space. The full name of this data structure is a reduced order binary decision diagram, or ROBDD, but it is often called just BDD. It is reduced because isomorphic subgraphs are combined together. It is ordered because there's a total order between the variables that appear on the path. In this BDD, the order is that x1 is smaller than x2 smaller than x3, which means that in a path, x1 appears before x2, which appears before x3. A path from the root to a leaf in the BDD corresponds to an assignment of Boolean values to the variables of the BDD, in this case x1, x2, and x3. 0 is assigned to a variable if we exit a node which is marked with that variable to the left with a red dashed line. And 1 is assigned if we exit that node to the right with the blue solid line. Later we will skip some of these conventions, but it would be clear which variable is assigned a 0 and which one is assigned a 1. However, not all the variables need to appear on every path. For example, on the path that is emphasized on this slide, the variable x2 does not appear, only x1 and x3. In this slide, x1 is assigned to 0, x2 is assigned to 1, and x3 is assigned also to 0. And the function returns for this assignment a 0 or a false. In this slide, the emphasized path is again the one that does not include x2. The value of x1 here is 1, and x3 is also 1 because we exit the nodes x1, x3 in this path with the right blue full line. The value of the function when x1 is 1 and x3 is 1 does not depend on the value of x2. It could be either 0 or 1, and the function would return a 1. The construction of Boolean trees and BDDs corresponds to Shannon's expansion, which says that the function equals a disjunction of two cases. The left case is when we restrict the value of one of the variables to 0 or false, and the right case is when we restrict it to 1. We splitted our BDD according to Shannon's expansion based on the value of the variable x1, which is in the root. The left part corresponds to x1 equals 0, and the right part corresponds to x1 equals 1. Note that there is a lot of commonality between the two parts. So let's take the right-hand part, and we'll split it again according to Shannon's expansion based on the value of x2. So we obtain again two subgraphs. The left part is the function where x1 is restricted to 1 and x2 is restricted to 0, and the right-hand side corresponds to x1 restricted to 1 and x2 restricted to 1 as well. So let's recap. A BDD is a directed acyclic graph representation of a Boolean formula. Each leaf is labeled with either a 0 or a 1. Each non-leaf node represents a variable. The variables appear on every path according to the same order, although not all the variables need to appear in every path. If we exit a node that is labeled with some variable in the left red dashed edge, then that variable is assigned a 0. And if we exit on the right with the blue solid line to the right, then that variable is assigned a 1. So the left successor or the red successor is called the low successor, and the right successor or the blue successor is called the high successor. Low because it is 0 and high because it is a 1. And then if we follow that path, then we get the value that the function represented by this BDD returns for that assignment. That value is independent of the values of the variables that do not appear in the path, and labels the leaf node of the path. The binary tree in this slide is not an ordered binary decision diagram, and the reason is that the variables do not appear on the same order in all of the paths. The tree in this slide is an ordered binary decision diagram. However, it's not reduced. There are subtrees which are isomorphic to each other and they appear several times. So what we need is a way to combine isomorphic subgraphs, and we work bottom up from the leaves to the root. We can combine all the leaves with the same values. So we need at most two leaves, 0 and 1. If the low and high successors of a node are the same, then the value of the function does not depend on the value of the variable in that node. So we can remove it. We can redirect the incoming edge to point to its successors. According to the third reduction rule, if we have nodes that have the same low successors and separately the same high successors, then we can combine them. We cannot apply here any further reduction rule, so we're done. We have a reduced form, and notice that the reduced form is unique regardless of the order of applying the reduction rules. Different variable orderings change significantly the BDDs. In this example, there's a function such that according to one ordering, in which the variables appear in ascending order, x1, x2, until xn, the growth, depending on n, is linear. On the other hand, if first the variables that are odd appear, and then the variables that are even, then the BDD grows exponentially with n. In addition to compactness, the BDDs are equipped with procedures to combine and transform them. The first operator we'll see is the restrict operator. It replaces a variable by a constant, 0 or 1. Restricting x to 0 is done by redirecting the incoming edges of a node that is labeled by the variable x to its low successor and then removing that node. And similarly, for restricting x to 1, its incoming edges are redirected to its high successor and then x is removed. Then we may need to reduce the BDD. Here we restrict b to 1. Note how we need to redirect its incoming edge to its c successor, which is the high successor. We start with the left b. After we worked out the left b and it is removed, we need to work out the right b. And now we work out the remaining b, which is the right b. And we're done. In general, we need to apply the reduce operator in order to reduce the BDD, but in this case, the BDD is already reduced. Let's see now how to apply a Boolean operator on two BDDs. So f and g are two Boolean functions that are represented using BDDs, and we want to combine them using a Boolean operator, which we denote by hashtag. And hashtag can stand for AND, OR, XOR, or any binary Boolean operator. Recall the Shannon expansion. It says that a function can be decomposed into two disjuncts, where the left part is obtained by restricting some variable to the value 0, and the right part is obtained by restricting it to 1. In addition, we know that restrictions distribute over Boolean functions. We obtain a formula that can be read intuitively as follows. In order to calculate f hashtag g, we need to apply hashtag recursively on the low successors of f and g respectively, and on the high successors of f and g respectively. When f and g are Booleans, meaning that they are leaves, then we just apply the Boolean operator, whether it is AND, OR, XOR, NAND, whatever. We need to take care that not all variables appear on each path in the two BDDs. The procedure receives two nodes in the two BDDs, and initially these are the nodes for the root of f and the root of g. So here's the recursive procedure apply, where hashtag stands for any binary Boolean operator. When both parameters are leaves, we just apply the Boolean operator on the value of these leaves and return a leaf with that value. When the parameters are non-leafs that are labeled with the same variable, let's call it x, then we apply the procedure recursively. First, with the low successors of the two nodes, and then with the high successors of the two nodes. These results will become now the low and the high successors of a new node labeled with x. The case where the variable that labels the first parameter comes before the variable that labels the second parameter in the variable order corresponds to the fact that the second parameter is on a path that does not depend on the first variable. In this case, the recursive calls use the successor of the first parameter and not the successors of the second parameter. The second parameter stays put. And of course, there is the symmetric case. A naive application of the above recursive procedure may result in recalculating subgraphs again and again. In fact, the complexity could be exponential in the size of the BDDs. On the right-hand side of the slide, we marked subgraphs that are the same with the same color. So there are pink subgraphs and green subgraphs, blue subgraphs, and black subgraphs. In order to solve that problem, we use a dynamic programming principle called memoizing, where each time that we calculate the function with two parameters, we keep the result of that calculation, and next time that we reach a call with the same parameters, we do not calculate again, but use the old result. This allows us to reduce the complexity of applying a Boolean operator on two BDDs into twice the multiplication of their sizes. Now, as in all the operators that we presented so far, after completion of the procedure, the BDD may not be reduced and we need to apply the reduce operation. Given a BDD that represents the Boolean function phi, we can easily generate a BDD that represents exist x phi. We do that as follows. We first take the restriction of phi where x is restricted to 0, then we take the restriction of phi where x is restricted to 1, and then we apply the disjunction on these two BDDs. BDDs represent Boolean functions, and Boolean functions can be expressed using propositional logic. In propositional logic, adding existential or universal quantification over Boolean variables does not change the expressive power. However, sometimes it's useful, for example, to present some Boolean function in a more compact form. One of the claims for fame of BDDs is in model checking. What is model checking? We have a system, which could be software or hardware, and we have a formal specification, which is given with some specification formalisms such as a temporal formula or an automaton or process algebra, and we want to see if the system satisfies each specification. We want to verify it in an algorithmic way, and we want to cover all cases. If the system does not satisfy its specification, then often we are interested in obtaining a counterexample that will allow us to understand why this is the case. So let's consider a concurrent program which appears on the left of the slide. It consists of two processes, and the intention is to solve Dijkstra's mutual exclusion problem. So each process consists of 4 lines, and inside a loop, each process wants to enter its critical section which is labeled with CR01, depending on the process, 01. And in order not to enter at the same time, it uses the variable turn, such that turn equals 0 when process 0 can enter its critical section, and process 1 enters its critical section when turn equals 1. So model checking is about verifying a system like this program against a specification, but already the name model checking suggests that what we verify is a model of the system. We need to model the system, and we see on the right a state graph that consists of all the states that are reachable from the initial states of that system, where both processes are at the head of their loops. There are two initial states because turn could be either 0 or 1 initially. And the graph represents how we move from one state to another by executing some atomic transition. There is a variety of specification formalism. And here we're going to look at the specification formalism, which is called computation tree logic, or CTL. The system is supposed to be modeled as a tree. This is an unfolding of the state graph that we saw in the previous slide. So we start with an initial node and then look at its successors and their successors and their successors, and we obtain a tree that can be an infinite tree from the state graph. Let's look at the specification EGP. EG is the temporal operator. E stands for there exists a path from the current state, and G stands for all the states on the path. So EGP holds in the state if there exists a path from that state on which all the states satisfy P. AFP means that in all the paths that start in the current node, there exists a node that satisfies P. So A stands for all the paths that start at the current node, and F stands for there exists a node on the path. EFP means that there exists a path on which there exists a node that satisfies P. There are other model operators, and we also can combine formulas using the Boolean operators and, or not. Let's look at the following state graph. The states are marked with the propositions I for an initial state and B for a bad state. The property that we want to check is whether bad states are reachable from initial states. This corresponds to the CTL property I implies EFB. We start with the states that satisfy B, and we work our way backwards. In each round, we had the immediate predecessors of the nodes that exist in the previous round. So we can work with two sets of states, the previous nodes and the new nodes, where the set of new nodes include the previous nodes. We're after the first round, and we're not done. We do another round and add more predecessors. We repeat these rounds until there are no more new predecessors. So if we work with these two sets of states, then we stop where the new states and the old states are the same. Now we check whether there are initial states that are included in the states calculated before for EFB. And in this case, all the initial states, all the yellow states, are included. So the answer is yes, there are states that are bad, that satisfy B, that are reachable from the initial states. In fact, from every initial state, a bad state is reachable. Some comments about the procedure. First, we need to build the state graph. This can be done using depth first search starting from the initial states. The problem is that we go state by state from the initial state, and we need to cover all the reachable states. Then we can apply the algorithm. Now, the procedure that we showed can be generalized to the logic CTL. The different subformulas can be worked out bottom up, starting from the subformulas, and then based on the marking of nodes with subformulas that are satisfied by them, we can go on and calculate bigger subformulas until we mark whether each node satisfied the entire CTL specification or not. An important comment that at this point may look unimportant is that we could have performed the same thing not only on the reachable states. So suppose we added some states that are not reachable, like the 4 ghost states that appear on the left. We could apply the same procedure. That would not change the results, but this would be important when we see how to deal with BDDs. We see here in the box the pseudocode for the model checking procedure that we described. Model checking was invented concurrently by Emerson and Clarke, and by Quille and Sifakis in 1980-1981. The procedure that we see here uses the 2 sets of states, x1 and x2, and it is easy to generalize it to other CTL properties. The main obstacle is that when we process states one by one, then we are limited in the number of states that we can process, both in time and in space. Suppose, for example, that we have 4 variables, each one with 32 bits. Then we need overall 128 bits. So we need 2 to the power of 128 states, which is about 3.4 with 38 zeros after them. This is a lot of states. We cannot enumerate all these states. We cannot store all these states. For that, we can use symbolic model checking using BDDs. Although we're interested here mostly in runtime verification, the description of symbolic model checking using BDDs would serve us to understand representation of states using BDDs and later the runtime verification algorithms that are based on BDDs. Symbolic model checking using BDDs were introduced by Birch, Clarke, Macmillan, Dill, and Wong in a seminal paper in 1990. The following procedure is very similar to the procedure we saw before, only that we replace sets of states by BDDs representing sets of states. So we replace x1 and x2 by 2 BDDs, fx1 and fx2. And we also have BDDs to represent the set f of bad states and the set I of initial states. Putting the state-based pseudocode near the BDD-based pseudocode, we see how similar they are. It's really almost a direct translation where sets of states are translated to BDDs and operations on sets are translated into Boolean operations on BDDs. Intersection between sets is replaced by conjunction between BDDs. And union between sets is replaced by disjunction between BDDs. And this is performed using the apply conjunction and apply disjunction. R is a BDD that represents the relation between the current states and the successor states. We'll describe later how to construct it. It is defined over pairs of states. We want now to represent states using BDDs. So state is an assignment to the program variables, including the program counters. So we encode each value as a bit vector, and if we have several variables or several values in the assignment, then we concatenate the bit vector. So let's see, for example, the two states where in the first one x is 0 and y is 0, and in the second one x is 1 and y is 1. So the first bit vector is all zeros, and the second bit vector consists of concatenation of twice 0, 0, 1, which is the binary representation of 1. Here's a BDD that corresponds to the first assignment. It returns 1 exactly when all the bits are 0. Note that here the low edge is the dotted one and the high edge is the full one, but we didn't use the left-right convention nor coloring with blue and red. And here's a BDD that returns true or 1 exactly for the assignment 001, 001. The BDD on this slide returns 1 if the assignment is either the first or the second. Returning to the pseudocode, the relation R is very important. It represents the relation between the
We shall now explore the use of BDDs in runtime verification, and in particular runtime verification with first-order pastime temporal logic. The challenge is to monitor events that carry data, such as integers, floating point numbers, strings, etc. That is, not just Boolean propositions. Let us first put runtime verification into context. One can generalize the problem to that of verifying that some program or system satisfies a formal specification of its intended behavior. We thus have a program and a specification. In general, we can perform runtime verification of any system producing observable events. One approach is static analysis, for example, theorem proving, where we do not execute the code but use its structure to carry out a deductive argument. We can include model checking in this category. The alternative approach is dynamic analysis, where we execute the code. Here we interact with the inputs to the program and the outputs from the program. More specifically, this includes test input generation from specifications, also referred to as model-based testing. And it includes runtime verification, where we focus on monitoring the outputs of the program. Outputs can include events generated specifically to support monitoring. If we compare to model checking, in model checking we check infinite execution traces exhaustively, whereas in runtime verification we check finite prefixes of an unbounded execution. At any point in time we have observed a finite trace, but as the execution continues, this trace is expanding, hence the term unbounded. Note that runtime verification techniques can be applied to logs produced by a program. This is also referred to as offline monitoring. In a typical setup for a runtime verification architecture, a property formulated in some formalized logic is translated into a monitor. The system to be monitored is then instrumented to emit events to the monitor. The monitor can emit verdicts as a report, or it can provide feedback to the running system that the property has been violated. Work on runtime verification is usually concerned with optimizing one or more of the following dimensions. The monitor has to be efficient, both time-wise and memory-wise, and have as little impact on the running system as possible. The specification logic should be as expressive as possible, permitting the user to express the properties required. And finally, it should be as easy as possible to write and read specifications written in the logic. In this presentation, we shall focus on past-time temporal logics. The algorithms we will present work specifically for this case. We start with propositional temporal logic, since it lays the ground for the BDD-based algorithms for the first order case. In the propositional case, a trace is a sequence of Boolean propositions. The following two formulas are examples of propositional past-time temporal properties. The first formula states that whenever a close event is observed, then in the past an open event must have occurred. We assume that this property is checked for every new event in the trace. There is an implicit box operator in front of the formula stating that the property must always be true. The second formula expands on the first by demanding that in case a close event is observed, then in the previous state it must hold that there was no close event since an open event occurred in the past and that such an open event did occur. Let's look at the syntax and semantics. A formula in the core form is either constant true, a proposition, the conjunction of two formulas, the negation of a formula, the previous state formula stating that the argument formula holds in the previous state, and the since formula stating that the formula psi, the right argument, must hold in the past, and since then phi, the left argument, must hold. This is reflected in the semantics that you see in the lower left corner. The definitions are standard and define when a trace sigma in a position I satisfies a formula. We explain the last two. The formula previous phi is true if phi is true in the previous state. The semantics of phi since psi is true if there exists a trace position j such that psi is true in that position, and for all later trace positions k, phi is true. At the bottom we see the definition of when a finite trace satisfies a formula. A finite trace satisfies a formula if it is true in all positions. To the right we see a set of derived formulas, the standard Boolean ones and then the last two. Past phi, the letter p, meaning that phi is true sometime in the past. And history phi, the letter h, meaning that phi is always true in the past. Let's now look at the approach for monitoring such propositional past-time formulas. We first observe that the semantics of the since operator satisfies the equation shown in the blue box. This equation states that the formula phi since psi is equivalent to the following formula. Either psi holds now or phi holds now and phi since psi was true in the previous state. As can be seen, we are only concerned about values of formulas in the current state and the previous state. This observation led to the monitoring algorithm presented in the following and described in the shown publication below. Let us look at the evaluation of a very simple formula against a very simple trace. The formula states that close is true now and in the previous state open was true. Note that such a formula can change value back and forth between false and true as the trace is processed. In the lower left corner we see an abstract syntax tree representing the formula. The formula is here broken down into its subformulas. The subformulas are numbered from 0 and up, with the highest numbers lowest in the tree. This is later used in the algorithm. We now observe the first event, which is an open. The subformulas evaluate as shown. The close formula evaluates to false, this is node 1. and the open formula to true, this is node 3. But the previous open evaluates to false, this is node 2. As a result, the whole formula evaluates to false. We now observe the second close event. We create a new abstract syntax tree of the same shape and evaluate our subformulas in that. The nodes evaluate as shown. Note how the evaluation of node 2, evaluating previous open, looks up the value in the previous tree. The actual implementation uses two arrays, pre and now, indexed by the numbers assigned to the subformulas, for storing the Boolean values of the subformulas. As we see later, we use the same algorithm for the first order case, but storing BDDs in the nodes instead of the Booleans. The BDDs represent sets of assignments of the variables occurring free in the subformulas. The monitoring algorithm is here shown. It works on two arrays, pre and now, indexed by the numbers assigned to the subformulas. Initially, in step 1, all array entries in the now array are giving the value false. In step 2, we observe a new event. In step 3, we assign pre to become the now of the previous step. In step 4, we evaluate the subformulas. The purely Boolean subformulas have their obvious interpretation. Note that these only refer to the now array. The interpretation of the since formula is expressed exactly as the equation on the previous slide. Now phi since psi becomes now psi, or now phi and pre phi since psi. That is, we look up the value of phi since psi in the pre-array. Similarly, with the previous phi formula, we look up the value of phi in the pre-array. In step 5, we go back to step 2. On this slide, we show how the formula just discussed can be translated into code, as explained in Havelund and Rousseau 2002. We declare the two arrays and evaluate a formula by evaluating the subformulas bottom up, from higher formula indexes to lower. We see specifically the assignment statements. Now of 2 is assigned pre of 3, going back in the pre-array, and now of 0 is assigned now of 1 and now of 2, just referring to the now array. We have now presented an algorithm for propositional pastime logic. With this, we can monitor properties like the one shown. When a close is observed, we should have seen an open in the past. Suppose we refer to the opening and closing of files. Such a formula can only refer to one file. One could, of course, for each file of interest, introduce open and close events and write a corresponding number of properties. However, this is not only laborsome, but also impossible since file names cannot be predicted. The solution is to introduce a first-order logic allowing predicates over data and quantification over such. Here we express the more general property that for all files f, if we observe a close of file f, then we must have seen an open of f in the past. The syntax of the first-order pastime temporal logic is shown here. The difference from before is as follows. Instead of being just a proposition, a formula can be a predicate of data, either represented by variables or by constants. We also introduce existential quantification over data variables. These concepts will be explained in the following. Also shown are two formulas in the logic, similar to the ones we saw before, but now with file IDs as arguments.